Hi, my name is Ian Fogarty. I'd like to talk to you today about rings in organic chemistry. The first set of rings that we're going to look at are called cycloalkanes. They get the prefix of cyclo. They have 1 degree of unsaturation for every ring, and there's something that we're going to talk about called ring strain. And so here we have an example of a ring. It's got 3 carbons. It's got 3 carbons. There would be a hydrogen here, and a hydrogen here, a hydrogen, and a hydrogen, hydrogen, and a hydrogen. And so you would have C3H6. We would call this cyclopropane. Likewise, this would be cyclobutane, cyclopentane, and cyclohexane. So just adding cyclo on the front of however many carbons there are, ending in A and E. Unsaturation in rings. In order for you to create this ring, we've got 6 carbons, 1, 2, 3, 4, 5, 6. You'd have to start with an alkane, so you'd have CH3, CH2, 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 CH3, and you'd have to go and remove that hydrogen right there and that hydrogen right there in order to form a long bond all the way to there to form your ring. And so there are 2 hydrogens that are missing in this case. There are 2 single bonds missing, and so that would represent 1 degree of unsaturation. It really should be C6H14 if it's going to follow the CnH2n plus 2 rule. But because it's missing 2 hydrogens, so it's got 1 degree of unsaturation per ring. Now there's something called ring strain that we need to ponder. So if we were to have a triangle, like cyclopropane, we would have an equilateral triangle. The bond angle in here is going to be 60 degrees. This is a problem because these are still sp3 hybridized, and sp3 hybridization would like to have 109.5 degrees. And so what we're doing is we're forcing something that wants to be 109.5 and making it be 60, and that's not particularly good. And so this thing is called ring strain, and as a result, cyclopropane is not very stable at all. It doesn't last very long. It's very easy to break. If we look at cyclobutane, we're looking at 90 degree angles, and so it's a little bit more stable because it's a little closer to 109.5, but it still has significant ring strain. And again, this doesn't last very long as well. Now, if we look at cyclopentane, we have a better situation because the bond angles for cyclopentane want to be 108 degrees, which is very close to the 109.5, and that's even if it's just a flat two-dimensional surface. Turns out that you can also have this kind of envelope shape. This little envelope shape where it's kind of flat on 4 sides and then it's got this little lip on here. And so because of that, you can get to almost exactly 109.5. As a result, there's very little ring strain in cyclopentane, and 5-membered rings are wonderful. They're found everywhere, they're very stable, and they're great in biology. Cyclohexanes are very stable. They have virtually no ring strain at all. When you look at cyclohexane from the side, you have 2 kind of conformations. One where you have this chair kind of shape. It looks like you could maybe put a person in here. Looks like maybe you could put a person lying in a lazy boy here. And a boat. It looks more like perhaps a canoe, where you could be sailing the 7 seas. It turns out of the 2 of these, the chair conformation is generally more stable than the boat conformation. In order to switch between the 2, all I have to do is take this bottom piece and let it fold up. And this happens fairly often. It's possible to have rings with branches off them, and so if we were to name them, we would name the ring as the parent chain and then the branches off of them. So in this case, we would have for the ring 1, 2, 3, 4, 5, 6, and that way the branch has the smallest possible number, and we have 1, 2, 3, 4. So this is going to be butyl cyclohexane. This one, 1, 2, 3, 4, 5. So it's going to be cyclohentane. And then the branch is going to be 1, 2, 3, isopropyl. One, two, three, four, five. I'm going to prefer that one. I could have also chosen to go this way. 1, 2, 3, 4, 5. But if I did that, then in this case, the ethyl group will get a 1 and a 1, whether I go with the blue numbering or the red numbering. However, if I go with the blue numbering, the second ethyl branch gets a 4, whereas if I go with the red numbering, the second ethyl branch gets a 3, and so it's better. So this is going to be 1,3-diethyl cyclopentane. Now looking at cycloalkenes is a little bit different. We need to worry about which way we go here. It turns out that a double bond is going to start at carbon number 1 and go to carbon number 2. And that might seem reasonable and obvious in cycloalkanes, but in cycloalkenes it may not be. So this has got to be a 1 and that's got to be a 2. If it starts on carbon number 1, it's got to go to carbon number 2. And so this is just going to be cyclopentene. We could put a 1 in front of it there. And so over here we would want to have 1, 2, 3, 4. We could not go and do this 1, 2, because my double bond doesn't start at carbon number 1 and then go to carbon number 2. So this is going to be 1, 3 cyclopentadiene. And this actually shows up a bunch in organic chemistry. We can look at multiple cycloenes. And so here would be 1, 2, 3, 4, 5, 6. That would be 1 cyclohexene. 1, 2, 3, 4, 5, 6. This would be 1, 4 cyclohexadiene. Compare that to 1, 3 cyclohexadiene. And then this one is going to be a special ring. We'll name it here, but there'll be a whole video dedicated to just this one. 1, 2, 3, 4, 5, 6. This is going to be 1, 3, 5 cyclohexatriene. And in fact, there's something wrong with this name. This is the right name to describe that structure, but it's so prevalent and so special, it gets its own name. And so we don't actually call it 1,3,5 cyclohexatriene, we call it something else. Thank you very much for your time.